Assalamualaikum warahmatullahi wabarakatuh. We meet again virtually. Okay, so today we will continue our part 2 for chapter 4, which is the straightening mechanism. So before I proceed, okay, I would like to recall a little bit about what we have learned last week. So last week you have learned about the dislocation. Okay, so this dislocation. Okay, so you have know that this dislocation will make your crystal weaker, right? So why we say that if the crystals happen to have dislocations, so they are weaker. Why? Because it forms plastic deformation. It means that the crystal is not the arrangement of the atoms for that crystal is not similar as the original crystals. Okay, that's why it will form plastic deformation. Okay, but okay, if we try to hinder the dislocation motion, if this dislocation being hindered, okay, being hindered, or we can say the dislocation motion being stopped, okay, so what happens? So the crystals, okay, so this crystal will tends to behave have the properties of stronger crystal. So when we say the dislocation being hindered, so it means that the crystals will have this straightening effect or straightening mechanism. So why, okay, why this straightening effect, okay, is very useful in alloys. Okay, why is that? Okay, because strength is the most crucial aspect in an alloy. So okay, so why we say strength is the most crucial aspect? Because when you have a stronger metals or the stronger alloys, okay, so when you have a higher or stronger strength, okay, so your alloys or your metals may carry more, okay, carry more load. Okay, so that's why, okay, straightening is very important aspect. So when you look at your previous slide, okay, so you can find there are a few types of straightening mechanism. Okay. Okay, so there are a few types. So number one, okay, we will look at the grain size hardening. The second one, we will look into solid solution alloying. And number three, we will look into strain hardening. Okay, so we will cover this three mechanism only. Okay. So when we talk about straightening mechanism, okay, why? Because we want to have a stronger alloy. Okay, why we want to have a stronger alloys? Because if you have a strong alloys, so that alloys can carry more loads. Okay, so the type of strength, okay, that we will look into the mechanical strength, okay, and then the yield strength, and as well as the hardness. So these are the types of strength. Okay, this is a type of strength. Okay, so don't get confused. So these are strength type. Okay, the mechanical strength, the yield strength, and the hardness. So if you have higher mechanical strength, so it means it's a stronger alloys in mechanical. If you have more hardness, so it means that it is still a stronger alloys. Okay, while these, so while these are the straightening mechanism. So how the straightening being conducted or being observed or being applied. Okay, so these are the mechanism. Okay, now we will look into the summary of grain size reduction. You can also find the terms grain size hardening. Okay, so before we proceed, again let us recall a single crystal structure. So this is a single crystal. Okay, so this is single crystal. And then we draw another structure, which is a polycrystal. So this is the so this one is the polycrystal. So if you compare the single crystal structure and the polycrystal structure, so this one I'm sure all of you have known. So for the single crystals is what we always imagine in crystals, where you will have the same or similar orientation. Okay, so you have a similar orientation of the unit cell. While if you look at the polycrystals, what you can find, so of course the orientation of the unit cells are different. Okay, so this is the real crystalline material. Okay, and then the orientation of your unit cell is not rigid as the single crystal. So the orientation of the unit cell change, as you can see there, change from region to region. Okay, what I mean by from region to region is, as you can see, this one, at your polycrystal structure. Where is my cursor? Okay, so let's change the color. Okay, so as you can see, at the polycrystal structure, so this is the one region, or one unit cell, and this is another one, and this one is another one. So this change of the orientation, the changing of the orientation from 1 to 2, for example here, because of these boundaries. Okay, yeah. Okay, so because of these boundaries. So these boundaries, okay, we term it as grain boundaries. Okay, so we have discussed the grain boundaries in your last week chapter. Okay, so these are the grain boundaries. Okay, and then we try to imagine if these crystals have slip plane. Okay. Okay, for example, this is the single crystal, and this is the colors. We try to change the color. Okay. Okay, so imagine this is the slip plane of this single crystal. Okay, so it goes that way. Okay, and this is the slip plane. So when these single crystals, okay, have a slip plane and it will moving, betul? And it will create what we call as the slip system. Okay, and when the crystals, okay, have that behavior, okay, and then it will create one slip step. Ingat lagi tak? Okay, so you will have one slip step. Okay, then we say this crystal, this have dislocated, so these crystals have deformation and so on. Okay, so what about a polycrystals? Okay, so in a polycrystal, so if you have a slip plane, okay, sama, so slip plane. Okay, so this is a slip plane for this particular unit cell. Okay, so remember, for the polycrystals, the orientations are changed from region to region. So this may be the slip plane from 1, but it stopped at the grain boundaries. And then, for example, for grain number 2, this is how it slipped. Okay, and then it can move further because they have grain boundaries. And this is the third unit slip plane. Okay, so actually, okay, when you see these diagrams, okay, so you can see these grain boundaries. Okay, these grain boundaries are blocked. Okay, they block, okay, the what we call orientation of slip plane. So this slip plane blocked by these grain boundaries. So that's why, okay, you cannot see any, for example, slip steps, okay, such in these single crystals. Okay. So what we can say, what we can conclude, okay, so the grain boundaries act as obstacle, okay, to the dislocation motion. Okay, so clear, because of the grain boundaries. Okay, and then we look at two types of polycrystals. Okay, try to look at these two types of polycrystals. So we have one polycrystals, okay, and this is the unit cell, so it still have grain boundaries here. Okay, so and we have another this color. Okay, so we have another okay, polycrystals, and this is how it looks like. Macam mana nak lukis? Okay, so what's the difference between the first polycrystal and the second polycrystals? So the first polycrystals, okay, you can see a coarse grain, okay, a bigger grain, while for the second polycrystals, okay, it has a finer grain or smaller grain. Okay, so again try to imagine, okay, if these two polycrystals, okay, have slip plane, okay, similar with the top example, okay, so they have slip plane, okay, and these also have slip plane. Okay, so what we can compare with the finer grain, you can have more grain boundaries, correct? You can have more grain boundaries in finer grain. From this example, okay, for example, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12 grain boundaries here. For the coarse grain, for this one, I bet it will be higher than 12 grain boundaries. So this one is simple observation lah. Okay, so the finer grains will have more grain boundaries. So when you have more grain boundaries, okay, more grain boundaries, then you will have to have more dislocation obstacles, correct? Okay, because these grain boundaries is actually act as the obstacles to the motion, to the dislocation motion. So when you have more grain boundaries, so you will have more dislocation obstacles. So with that, okay, you will have ataupun you will require more stress, okay, to be applied in order for these materials, okay, create plastic deformation. Maksudnya for these materials to be broken in, or for these materials to have a slip, okay, so it will require more stress. Why it require more stress? Because they have more dislocation obstacles. Okay, ada banyak penghalang. So that's why if you want to remove all the penghalang, so you have to put more stress. Okay, so with that, okay, we can say that with finer grain polycrystals, they have higher strength than the coarse grain, and of course then the single crystals. Okay, next, the second mechanism, which is the solid solution alloying, or known as solid solution hardening. Okay, or known as solid solution hardening. Okay, so from previous week, okay, so you have know what is solid solution. So solid solution, okay, is categorized with two characteristics, which is the first one, the interstitial, okay, and second one is substitutional. Okay, so for these two properties, or these two characters, the interstitial and the substitutional, okay, they are both, okay, relates to higher strength of crystal. Okay, or those who have these two solid solutions properties will have the crystals will have more strength than the single crystal or the pure crystal. Okay, so why did I say they behave like that? Okay, so again we look at the single crystal. So this is a single crystal where you have atoms, okay, arranged, okay, in a very periodic way. Okay, so this is your single crystal. Okay, if you substitute one of your single crystals here, okay, with another atoms, then you will create a crystal that looks like this. Okay, so for example, you substitute one of the atoms here. Oopsie. Okay, so you substitute one of the atoms, okay, from the single crystals, okay, with other atoms. Okay, and this, okay, really put a label. This is the substitutional, okay, solid, okay, system. So with this, when you substitute one of the atoms, okay, with another atoms, okay, so you tend, okay, to displace the atoms. Okay, as you can see here, the atoms has displaced. Okay, they have displaced. So when the atoms displace, okay, the original atoms, the atoms will displace. Okay, displace from the arrangements in the single crystals. So when the atoms displace, it will create, okay, a strain, okay, where we call it strain field. So it will create a strain towards the neighboring atoms. So don't need to use red color. Okay, so it will create strain to the atoms. Okay, so this strain, okay, will lead to the tensile stress. So when you have more, okay, when you have more, it's not more when you have a larger, for example, if you have a larger atom, okay, or when you have a larger size difference, okay, the size of the atoms, then you will create more strain. Why you create more strain? Because you have more atom displacement. So with that, okay, you can have a harder crystals. Okay. So that is example for the substitutional. Okay, if let's say you have interstitial, so remember interstitial when the atoms, okay, just fit in, or the atoms being placed in the hollow space between the atoms that been arranged in the single crystal. Okay, so when the interstitial atoms are larger, okay, than the hollow size, so the characteristic or the properties will be similar to the larger substitutional solute. Okay, so it will still can create strain field, and then it can make a harder crystals. Previously I have mentioned if you have a large size difference, then you will get higher strain. With this, you will lead to higher tensile stress. So when you have a higher stress, then your materials or your samples will tend to get stronger. Okay, so to have a clearer understanding about the statement, so we look at the graph here. So the X is the percentage of solid or concentration of the solid. Okay, so for example, this is 10, this is 20. So, okay, so for the Y is the tensile stress. The stress. Okay. Okay, so for example, this is 50, this is 100, 150. Alright, and then you have a few elements. Okay, so this is a graph for Sn with atomic radius of 1.51 Armstrong, and okay, we have here beryllium 1.12 Armstrong. Okay, and then the third element is nickel with the atomic radius of 1.25 Armstrong. And then the final element, for example here, is zinc with the radius of 1.31 Armstrong. And then we compare with copper. So copper has atomic radius of 1.28 Armstrong. Okay, so here, here you have a pure copper. Okay, let's say if you have zinc as a solid inside the copper. Okay, so zinc is the solid inside the copper, and when you can see the gradient is smaller, okay, or you can see the slope for this graph is smaller. So why is that happen? Because they have small size difference, or the radius of the atoms is at about the same. But here when you look at the percentage or the concentration of the solid, here if you have 10%, and then you compare with 20% of zinc inside the copper, you can find the stress are increasing. So when you have higher percentage of solid, the stress increase. So when the stress increase, again you will have a stronger material. Then we look at this 1 and 2 graph. Then we compare with the copper here. We compare the atomic radius. So even though the beryllium has lower or smaller atoms rather than copper, but what we can the thing that we have to look into here is the different value, not this smaller value. So the difference value between the beryllium and copper is 0.16 Armstrong. While nickel with copper, you have a difference of 0.03 Armstrong. That's why nickel, even though it is larger than beryllium, but nickel slope, the nickel graph slope is smaller than the beryllium, because you have to look the size different. So when you have a larger size, then your stress is higher. So when your stress is higher, then you lead to a stronger material. So in conclusion, for the solid solution, if you want to have a stronger material, then you have to increase the solid. Or you can choose a solid that has larger size difference. So strain hardening is also known as cold working or work hardening. So these are all the same term. when you read about strain hardening, okay, basically you will observe, okay, this crystal, okay, these particular crystals will undergo this location, okay, or it will undergo plastic deformation. Plastic deformation. Okay, so it means that the strain hardening, okay, is a concept of dislocation. Okay, but okay, as our in our previous slide, okay, we said that if a particular crystal undergo plastic deformation, okay, then this crystal tends to get weaker, correct? But how, okay, how or why the strain hardening, okay, is part of the strengthening mechanism. Okay, so to really understand, okay, this theory, so we have to look at a simple experiment. Okay, so the experiment is the stress and strain experiment. Okay, stress and strain, we will look deeper into this topic in our next chapter. Okay, so this is a stress and strain graph. So here is the stress. Here is the strain. Okay, so usually for materials, okay, we will get this type of graph. Okay, so if you look at the graph, you can observe there are two types of graph, okay, that we can observe. First, a linear graph. This region is linear graph. Okay, and this region, okay, this region is some sort of quadratic graph where they have curve. Okay, so for the linear graph, so this region we term it as elastic region, but we will look into this on our next chapter. And this region, okay, the quadratic graph is the plastic region. Okay, so the elastic region means that your materials, okay, when you put a stress towards your material, and then when you release the stress, it can go back to its original shape. While in the plastic region, when you put a stress onto your samples, okay, and then when you release the stress, okay, your samples won't go back to its original form. So it will form plastic deformation. So it will deform, okay, permanently. Okay, so we have a sample. Okay, so this is our sample. Let me draw a sample for you. And this is our sample. Okay, this is our sample. Okay, so it looks like this. Okay, so this is our original sample. Okay, and then you put a stress, okay, onto this sample. Okay, so you put a tension stress, and the stress is pulling away or pulling outwards of your sample, so that you have this stress, okay, towards your samples. So what happens to your sample? Okay, at this point, okay, at this range, here or here or here, they eventually, okay, this sample eventually will get back to the original sample, okay, or to the original shape. But let's say, okay, at this point, okay, so at that point, okay, so your samples may not form in its original um, samples, okay, or in its original shape. So it might form a plastic deformation. For example, it tends to get longer. Okay, it is longer. See, it is longer than the original form. Okay, so this is the we call PD. Okay, after it undergo plastic deformation, then it won't get back to its original form at this point. Okay, but even though it occurs plastic deformation, or even though it is deformed, but the sample are not broken. They are not broken. Okay, they are still intact. So we can say they can still be used. Okay, but in the longer length. Okay, so we did an experiment, okay, by forming, okay, the stress and strain, okay, experiment with this original component, and we are doing stress and strain experiment again with the plastic deformation component. Okay, so let's take a look, okay, both results. Let's look at the experiments here. Okay, you have original samples with a shorter length, and then you have a deformation sample with a longer length. And then we did a stress and strain experiment. Okay, so this is stress and this is a strain experiment. So from this graph, okay, as I previously mentioned, these are the elastic region, and then at this point, okay, where the curve or the graph begins to form a quadratic graph, so this point known as elastic region. Okay, so elastic point. So it means that below these points are elastic region. Okay, and then we try, okay, to run a deformation experiment. Okay, so from the original experiment, the stress and strain experiment, okay, so slightly above the elastic point, okay, where it is situated in the plastic region. So at this point, okay, we stop the experiment, and then we unload any stress, and then we have this deformed material, and this is the material. Okay, as you can see, the materials are the material is longer than the original samples. Okay, apart from the longer materials, okay, these materials are still intact. Okay, it means that it can still be used. Okay, and then at this point also we run, okay, the stress and strain experiment again. It means that these samples, okay, run another experiment, the plastic deformation samples. And what you can see is you still have this linear curve. Okay, so that linear, similar to the original curve, which is the elastic elastic region. Okay, and when you calculate the gradient, okay, from the original, and then you compare the gradient value from the deformation samples, they are the same. Okay, so these are the elastic point for the original sample. And then when you run, okay, so it should be here, right? But when you run again the stress and strain experiment, okay, for the deformation samples, you can see that the elastic point is changed to this point, okay, where the point that is in the deformation, or that is in the plastic region. Then after this point, then it will have the deformation region or plastic region. So this is the plastic region. Okay, previously in our previous slide or in the literature, we know that if you have a plastic deformation, then you have increased the dislocation density. So the dislocation density being increased. That's why you tend to get a deformation structure. Okay. If the dislocation occurs, okay, we say that the crystal or the samples are weaker. But if you look at the graph above, or the experiment conducted above, okay, you can see that from the original samples, okay, so let's say this stress value is 100, for example, and this value is slightly higher, 150. So the stress value for the deformation samples is higher than the elastic samples. So it means that the even though the samples undergo deformation or plastic deformation, the permanent deformation, okay, this structure is not considered weaker, but it is stronger. Okay, nampak tak? Okay, because the stress is higher. The stress to dislocate, okay, to have a higher dislocation is higher than the original stress. So it means that, okay, this, okay, you can say this statement is partially correct, okay, because in experiment, okay, we can see that with the deformation structure, the stress are higher than its original structure. Annealing is a heating process. Okay, to a deformed material, okay, to a deformed metals. Okay, why we need to heat this deformed metal? Because as we want to have, or we want to restore the properties because we want to restore the what we so call original properties. But this heating, this heating has its own rules. So this heating must be, the temperature must be above its recrystallization temperature. Okay, so the temperature must not, this temperature must not get the materials for the metals to melt. It means that these materials must not go further its melting point. Melting temperature. So you must not heat the deformed material until it's melted, just above its crystallization temperature. So that is annealing process. So why the materials, the engineers, wants to anneal those deformed material. Why? Because they want to restore the properties before the deformations. As you know, when it undergoes cold working, on the previous slide, so you tend to have, the materials tends to have a harder sample or harder materials, or the samples also tends to get stronger. But these materials will decrease its ductility. So in order to improve this ductility, in order to improve the ductility, so they try the annealing process. So then let's look at these two graphs here. The first graph is the cold working graph. Similar in your previous slide. So when these particular materials undergo cold working, then it will have increase in hardness. So the hardness will increase. And then apart from the hardness, the strength also increasing. So for example here, the strength is here. Oops. So this is the strength. Alright. But one properties will decrease. What is it? So the properties of ductility. So the ductility will decrease. So this is what your new materials will get. A more hardened material, more strength, but low in ductility. Then they try to perform annealing, or they try to put a heat to that particular cold working samples. But the heat, that is going to be support, is must not above its melting temperature. So it means that you must not melt the materials. Okay, so the temperature must be above its crystallization temperature. Okay, so what happens, okay, when you increase the temperature, okay, what happens to the hardness? Okay, so this is the hardness. And this is the hardness original point. Okay, and as you can see, when you perform annealing, and your sample will have that original properties. Okay, what about strength? So this is after it undergo cold working, and then when you have the annealing process, okay, and this is the original strength, okay, and when it undergoes annealing process, then you can have this you can restore its properties. Okay, what about the ductility? Okay, so this is the ductility. Okay, and this is the ductility point, and the ductility will increase. Okay, so it means that if you anneal your metals, then you can get, or you can restore its properties. Finally, this is the summary of annealing mechanism. So basically, it have 3 steps. 1, recovery. 2, recrystallizations. And the final step is the grain growth. As you can see here, when a material undergoes annealing, or when the deformation deformed samples undergo annealing, okay, the tensile strength will have, or will restore its original properties, or original strength, while the ductility will tend to increase. Okay, so what happened, okay, in the point of atomic perspective, okay, when annealing mechanism occur? So first of all, okay, when you look at the grains here, okay, when you look at the grains here, okay, in this region, when you look at the grain, okay, you can see different grain. Okay, you can observe different grain. So for the first part, okay, is where the recovery occurs. So what happened here? Okay, what happened to the grain here? Okay, so this is the first part. So what happened there? Those grain will relieve, okay, its internal stress. Okay. So when the stress relieved, okay, when the stress being relieved, so you can see some recovery of, okay, so you can see some recovery. So this is where the stress is being relieved. Okay, going further heating, okay, going further heating. So this is further heating, higher temperature. Okay. the grain becomes, or begins to reform. You see, the grain from here, from this structure, begins to reform to this structure, for example. So for the second step, okay, the grain begins to deform. Okay. we can say deform is macam defect. So the grains begins to reform. Because remember, annealing is you want to restore its own properties. Okay, so the grains begins to reform, and what happens? Okay, in the final step here, the grain growth. Okay, so when it is on further heating, okay, when you increase the temperature, then you can see the grains become larger. Okay, you can have a larger grain. So on the third phase, your large grain being restored. So it means that you get back your original structure. Okay, so the structure being restored to its original structure. So that is annealing mechanism.